Welcome, everybody. I hope this works. So, how many of you do know what is I/O virtualization? Okay, some. Cool. Thanks for coming. And this talk is going to be a little bit technical, but I promise that I can go into every detail of this issue because 45 minutes is not enough, but we will see. So, first, something about the project. So basically, I started something in September 2012. I was in an internship in Eurocom France, and basically, we wanted to do something on I/O virtualization security to see every aspect. How can we exploit? How can we do anything that is vulnerable? And one of these issues is presented here, and these are my own results, mainly my own results. But this is a part of a more complete work. So everything is going to be published later, but now I'm going to present just one small part of this. So first, we need to position I/O virtualization. We know that there is CPU virtualization, there is memory virtualization, and I/O virtualization. CPU virtualization is something when you expose computing resources to some VM by means of virtual CPU, and this VM basically uses computing resource to do computations in this isolated environment. Memory virtualization is really similar to this idea. However, you expose the memory resources to this specified VM by different methods. One such a method is called shadow page tables. It's a pure software implementation used by, for example, Zen. But there are hardware support for this. This is called extended page tables or nested page tables. And this is what is currently used. We know that hardware aspect is much faster. That is why there is a trend toward changing software implementations and use pure hardware solutions. I/O virtualization is a third member of this virtualization family. And here what we need is to virtualizing I/O devices towards guests. And these devices can be used by means of a virtual environment efficiently. So in this presentation, we are going to focus on I/O virtualization. If we want to understand what is the goal of I/O virtualization, we see a square here. Basically, there are four main aspects. Functionality. So basically, when you have an I/O virtualized environment, it has to provide a wide range of functionalities. It has to be compatible with different hosts. We know that in a cloud environment, we move different VMs between different hosts. And these different hosts have different devices. So basically, when we need to move VMs between different hardware, we want to guarantee transparency, so transparent device access. And this is what compatibility guarantees. Security is another important issue. So when we use I/O device access, it has to be secure. So we don't want to do really nasty stuff in clouds, right? So we have to be ensure that something is secure. And of course, performance. Performance is really important as well. So for example, when we use cloud computing in an environment and we, for example, want to run a web server or any kind of computing environment, we need this service to perform well. So we cannot use anything that is really low perform. Just for interaction, different types of solutions. Emulation, which provides really good compatibility. Basically, something is implemented in the hypervisor itself, and the virtual device, an emulated device, is exposed towards the virtual VM. And you don't have to change the device drivers inside a VM. So whenever you move these VMs between different platforms, you can use the same device drivers, and the emulated software will solve everything for you. However, the performance and the functionality will not be so good. To solve the performance issues, power virtualization was introduced. And by means of power virtualization, you have to modify the guest kernel. So you cannot use the same drivers that you used in emulation. However, if you can create a really small representation of the device that uses an exposed interface towards the VM, this outperforms emulation. And this is the only advantage of power virtualization. So, yeah. Direct device assignment is something that really important if you want to do something that performs really well. So direct device assignment allows you to access the device directly from the VM inside. and you can use the same driver that was originally created for the device that you bought in the shop. However, we know that direct device assignment has many security problems. Even more, when you have a direct device assigned environment, you don't have a memory overcommitment. It means you can use only those pages in the host that are pinned to the guest. So there is no such a thing when you merge pages and you use distributed pages between different guests. So you have pinned pages, and these pinned host pages are used by the guest, direct device assignment. And of course, there is other solution, shared device access, when you have virtual interfaces, and these virtual interfaces of the device can be used by the guest. So now we are going to focus on direct device assignment, which is also called pass-through, and we will see what we can do in this environment. So this is the threat model. This is the goal, what we want to do. In this presentation, I would like to do something like this. I have a controlled VM. I have a direct device assigned to a benign device, a pass-through device. So the firmware is not infected. Everything is correct. I can only control the VM, so I have root privilege in the VM. Anyone can buy such an instance in a cloud environment. So basically, you have root access. You can install the driver. You can modify the driver. But you don't have access to the firmware itself on the device. And all the protection mechanisms are enabled. Intel VTX means CPU virtualization, hardware-assisted virtualization, and Intel VTD2, which involves DME and interrupt remapping. I will let you know what is it exactly if you do not know. So something about the background. Interrupts in hardware virtualization. First of all, we have to talk about legacy interrupts. So these are the normal interrupts. These goes to the CPU via dedicated wires, and there are CPU pins, and basically you can interrupt the CPU by means of these signals, and the external devices use this kind of interrupt generation mechanism. Virtual interrupts are something that is used in virtual environments in VMs as the the device driver runs inside the VM. The virtual CPU has to be acknowledged about the interrupt handling mechanism. So basically, the virtual CPU is going to handle everything inside the VM. This is a theory, right? However, if you have a directly assigned device, there is a third mechanism. When you have a PCI Express device, there's a third mechanism, which is called message signal interrupt. And this is an in-band interrupt generation mechanism. So message signal interrupts allows an attacker, for example, to write to a specified physical address in the physical memory space. And as a result of this write operation, you can generate an interrupt. This is the theory. So let's see how it works. Originally, message signal interrupts were introduced by Intel as follows. You have to specify the address where the DMA write operation should happen. And this is initialized with 0xFEE, if you see the address field. And as I use the mark, there is a vector field as well in the MSI data field. And the vector itself specifies what kind of interrupt you want to initiate, what kind of interrupt you want to deliver to the CPU. And of course, you can specify what CPU are you interested in. If you are interested in just one single CPU, a bootstrap CPU, or application CPU, or you are interested in all the CPUs, so you can specify the destination mode as well. Just a small hint how modern architecture handles interrupt mechanisms. So basically, you have a CPU and cores, for example, and every CPU has a local APIC. APIC means Advanced Programmable Interrupt Controller. This is a mechanism that's used by the hardware to deliver interrupts toward the CPU and also to distribute interrupt requests between different cores. And of course, you have an IO APIC. You can see below. And this is something that's responsible for forwarding legacy interrupts toward the CPU. So this is how the architecture basically built up. We know that there are interrupt attacks. There are theoretical and practical interrupt attacks. These were mainly introduced by Invisible Things. They are really cool guys. They did a lot of work in this field, many hacks in I/O virtualization and virtualization security. You know many attacks from them. So the idea came from them that when you have a VM, and when you have a VM, you have a direct device access. The only known mechanism to achieve a message signal interrupt was using PCI configuration registers. However, these are virtualized, emulated by the system as well. So they figured out if they write by a modified eNeMI scatter-gather mechanism to a specified memory mapped I/O address, which is used for the local API-C, they can create a message signal interrupt from the VM via a pass-through device. So the eNeMI, we know that this is a direct memory access. So you can basically do a memory write or read operation from an I/O device without the intervention of the CPU. So this is something that we can use. And we know that DMA attacks were really widespread in virtual environments and in other environments. We knew that there are FireWire attacks, there are USB attacks, even there were DMA malware on the Northbridge. So come on, there are many attacks. That is why the hardware and Intel came up with solution that is called DMA remapping, for example, to stop this kind of attacks. So when you have a DMA remapping, basically these attacks are stopped because the source of the device is checked like a firewall. You have a filter, and if something comes from a device that is not allowed to do a memory write operation to a designated address, basically this firewall like DMA remapping stops the initiation. So this is how a local API-C, this is where the local API-C resides in the ingest environment. So the funniest thing that these registers, these API-C registers are memory mapped into the physical address space of the guest operating system. So you don't need to do anything to access a memory area, memory space that resides outside from the VM, but you can stay inside the VM and you see that the local API-C registers are mapped into your address space, physical address space, naturally. So, invisible things presented many attacks. Most of them were theoretical, but one of them was really practical, and they could really achieve a guest-to-hypervisor escape nonsense system. And the idea behind the attack was the following. You have a VM and a malicious driver, and they do a DMA write request towards the network interface card. They write into the local API-C, and as a result of the write operation, you initiate a MSI, a message signal interrupt towards the CPU. As there is compatibility format interrupt present, so you can specify the interrupt number. For example, if you specify that you want to create a hypercall, so hypercall is something when you want to access hypervisor level resources from the VM, hypercall happens in a virtualized environment. So if you specify explicitly that you want to create a hypercall, you just trigger this interrupt towards the CPU, and if the CPU executes this CPU executes the DOM0, which is a privileged VM, there is a chance that you can create a guest-to-hypervisor escape. So as you can see, this is a really nice attack, and it was presented. It was really cool. However, they put onto the last slides of their paper that this can be stopped. Cool, but interrupt remapping stops it. Interrupt remapping is something similar to DMA remapping, but you have a source ID. This is called bus device and function ID. So every interrupt generation is extended by a source ID of the initiator device, and this is verified by the hardware and the platform by a so-called interrupt remapping table. This is really similar to the DMA remapping table. So this is verified, and if the device is not allowed to generate interrupt towards the CPU, it is practically blocked. So this is how we are, and where we are, and so this is where this story begins. And the reason why they could do this is they redefined the format of message signal interrupts. This is not a compatibly format interrupt anymore, but it is a remappable format interrupt. And it is modified as follows. So you cannot specify the vector itself. You only have an address and a data. And in an address field, you can only specify a handle value. And this handle value is practically an index into the interrupt remapping table. So you trigger the message signal interrupt. And the interrupt remapping hardware checks if in the index what you specified, there is an entry. And of course, it checks if something, if the device is allowed to access something. And if the device is not allowed to access a resource of the CPU, basically the interrupt won't happen, so it will be blocked. So here we are. This is the state of the art. We know that we have DMA protection, we have interrupt protection, and we want to do something. We want to do something even when everything is turned on, and we think that our system is really secured. And let's see, what can we do? So now I'm going to present a new attack for the first time here at Hacktivity, and I hope you will enjoy it. But I will tell you that it has also limitations. So let's see. First of all, the idea was to implement a fuzzer to see what happens behind the curtains. So how can we really understand what kind of mechanisms there are at low level, and how can we really create NSI generation, and if there is any anomaly during this NSI generation. So I modified an Intel E1000E driver. This is a really popular driver. So most of the time, Intel devices use this kind of driver. And it is available almost on all the hardware. And I use this driver to create this fuzzer. So let's see the initialization phase of PT fuzz. This is the fuzzer, it's called. So the components, first of all, you have a VM. It has a virtual memory, and it has two buffers. A TX buffer, that is the virtual buffer that is used to store the bytes that you want to send. And the RS buffer is a buffer that receives the bytes you want to receive. You have a physical memory, of course, a guest physical memory of this virtual memory. You have a DMA remapping engine enabled, and you have a pass-through device. And this pass-through device has internal buffer, two internal buffers. One of them is for the send bytes. This is a TX, and the RX for the receiving bytes. So the very first step of the attack is putting the card into loopback mode. By means of this, you can enforce that something that you write is going to be received. So something that you send is going to be received by the same hardware. So this is the very first step of the initialization phase. Afterwards, as you can see, you fill the data, the MSI data, into the TX buffer. So this is what you want to write somewhere. This is the first step. After that, you just send it. You copy from the TX buffer to the RX buffer inside the pass-through device. And afterwards, and this is the most important thing, when you want to move, before you move this data, this NSI data, from the internal buffer of the device, you have to change the DMA operation, and you change the physical address where you want to move this payload. And actually, if the payload is moved to the local APIC memory map address space, this is something how you can generate this kind of message signal interrupt. However, as you can see, if I want to read or write a memory territory, a memory space that is outside of the assigned address space of the guest, the DMA remapping engine will tell, come on, guy, you cannot do this because I am a policeman, I'm here, I'll check all your operation. But as I showed you, this local APIC is mapped into the guest address space, so you can do this. Why not? So what PTFuzz does is it selectively fuzzes MSI address and data fields, and also changes the size of the DMA operation. So this is how it works. You have a guest VM, and you have the driver, and basically PT fuzzies any fields that I initialize. So let's see if I want to do a compatibility format MSI, I just simple fuzz the MSI data. Afterwards, I fuzz some field in MSI address space. Every time I create a pair and data and address pair, I just write to the local APIC and see what happens. So this is a manual fuzzer. I mean that in the sense that I create a payload, I write in, and I check manually if something happens, something weird happens. Of course, I'm not interested in any anomaly that happens inside the VM. I'm focusing on anomalies that happen outside the VM, outside, for example, in the DOM0, in the privileged guest, or in the hypervisor. All right. Examples for MSI, malform MSI requests. I saw that I can do some really weird behavior on the hardware if two conditions are met, any of them. First, if I specify an interrupt vector that is below 16, I can create an anomaly. Or if I change the size of the MSI request, I can create the anomaly as well. If I told you that ITL invisible thing said that the MSI request has to be specified as an exact dword size DME write operation. However, if it is not, something is going to happen. How many of you do know why is it important? Below 16. Because below 16, for sure, there are not interrupts, but exceptions in the interrupt descriptor table. So, what I saw after a while, if these two conditions or any of these two conditions are met, I saw that something in DOM0 or under KVM on the host, I saw that an eNeMI handler was executed. But how is it possible? As I told you, there is Intel VTX present, so virtual interrupts should work. There is interrupt remapping present, so nothing could evade a message signal interrupt. But somehow, a non-maskable interrupt handler was executed in the host or in the hypervisor as a result of malformed MSI request. And the funniest thing is, where does it come from? Is it a non-maskable interrupt which is delivered by a message signal interrupt, a compatibility format message signal interrupt? So in a compatibility format message signal interrupt, you can specify a vector number, right, in the data field. So you can say that I want to send a non-maskable interrupt with vector number 2. This is the vector number of non-maskable interrupt. Yes, but this behavior happens also if I specify anything that is below 16. Also, one can think that there are types of interrupts that was not detailed before. But you can specify it if you want to trigger a non-maskable interrupt, or you want to create a startup interrupt, or you want to create any kind of interrupt. So there is type of interrupts as well. But I realized that this is not something, it has nothing to do with message signal interrupt, but it was really tough to debug something that has no sign in the software, but something happens below it. Something happens in the hardware operation of the system. So I will come back later here, but let's see. So what I know, that I can create a non-maskable interrupt from a VM via pass-through device if I specify something malformed inside the payload. Later, I discovered something in the Intel manual about this. So it says software must guarantee that the field, it means that the vector field, the compatibility forward MSI data field, vector field is not programmed with the vector between 0 and 0f. So they explicitly say you cannot do something like this, but they don't mention anything why. What happens if you do such a thing? So what I saw after quite a lot of debugging, that the host bridge itself, something changes in the host bridge. And this is a system error status flag is set. System error. So how many of you do know what is it? System error reporting. So PCI devices generally support two kind of error handling mechanisms. First is called pair. This is parity error. This is something that is recoverable error. So if there is a transaction and something is bad with the parity or something like this, you can simply just retransaction and everything will go well. But if you get a system errors mainly refer to unrecoverable errors. So the funniest thing here is you do a system error via a software from the VM, and a host-side non-maskable interrupt handler is going to be executed. So the memory controller hub gets into the state of system error, and as a result of the system error, a non-maskable interrupt is generated, and this non-maskable interrupt is triggered to the CPU, and the corresponding eNeMI handler is going to be executed. All right, what we see? For example, on DOM0, we see that Xen eNeMI PCI system error. Nice. So on KVM, there isn't confused, but trying to continue. So this is something that should not happen. And the great thing in this is DMA remapping is defeated, right? Because we didn't do anything outside the guest physical address space of the VM. We did only an intra-guest DMA write operation. And one can say that, OK, you can still restrict the DMA write operation inside the VM. So basically, you apply intra-guest protection. However, we know that this is a really, really tough stuff to do some DMA protection inside the VM itself. Because inside the VM, for example, if you have memory locations that is overlapping by different drivers, and you want to separate one driver not to be modified by a DMA attack, for example, you cannot do this because it may happen that there are pages that are shared with other systems as well. And if this page is touched by something else that not belong to the driver itself, it's going to raise an error. So interrupt remapping is present, as I told you, but this is defeated. How? I create something like, seems to be like a compatibility format MSI request, but this is not that. Interrupt, the platform realizes that I want to create something that is malformed, so it blocks it, and basically blocks it before interrupt remapping happens. So interrupt remapping is there, but not there. And the second thing is that let's suppose that interrupt remapping is there. But what could interrupt remapping do with this issue? Interrupt remapping filters something that comes from a device that is not allowed to generate an interrupt towards a CPU. But what happens now is basically you generate a non-maskable interrupt that is generated by the host bridge, and the host bridge is basically allowed to access almost everything, because this is the host bridge. So first of all, interrupt remapping couldn't do anything with this. And the second thing, and this is the really important thing, as I told you, is non-maskable interrupt is not an interrupt, but an exception. From the perspective of the hardware, this is an exception because it has to be served instantly. Interrupt is something that is asynchronous. Basically, you create something, and you create an interrupt. And if the CPU has resources, it is going to be served. But a non-maskable interrupt is like an exception. It has to be served instantly. And as a result, in interrupt remapping, there is no, so when a non-maskable interrupt is generated, no source ID, no BDF ID is attached. So interrupt remapping engine cannot do anything. There is nothing to remap. So VMs. By the way, do you know what is virtual machine monitor? It's like a hypervisor. You know, hypervisor is the layer that resides between the VM and the hardware, and virtual machine monitor is an extended version of the hypervisor. It is capable of monitoring different VMs as well, not only one, and it can also share resources, do load balancing, and lots of things. So VMMs, I put VMMs because this is more general than a hypervisor. So theoretically, every VMM can be affected because this is not something that belongs to the software. It's more a hardware level issue. The attack is tested and verified on KVM and Xen, so for sure it works there. And, but it can happen that other VMMs are also affected. So why not? So what is the impact of this thing? We saw that we can do something that evades all the available mechanisms. And so what is the impact? So the first one is indirect DOS. A system hardware error is generated by software, and something is reported towards him. So no system admin want a buggy hardware behavior. So when I have a buggy driver, a buggy hardware, system admins want to change it, right? And if, for example, you are in a cloud and you have a pass-through device and the sysadmin sees that you basically have a device that is buggy, for sure he won't like it. So this is the indirect DOS version. Some systems are configured that cannot tolerate system error non-skippable interrupts. So basically, this is a system DOS. So for example, you can denial of service the entire system. And the third, what about privilege escalation? This is what everybody wants, right? So for sure, that host-side non-skippable interrupt handler was invoked. Basically, this is a guest-to-hypervisor escape. But how can you control the attack? So how can you really make it to be an exploit? And the answer is you have to find one simple software bug in almost every VMM. And if the software bug allows you to change, for example, the IDT, interrupt descriptor table, or you find something in the non-skippable interrupt handler that allows you to copy from guest to host. For example, invisible things invoked a hypercall handler, right? And in the hypercall handler, they had a function that allowed them to move memory content from the VM into the hypervisor address space. There was a copy from guest operation. And if something like this is inside the eNeMI handler, maybe you can cheat on this. Or you have a simple software bug that allows you to create an unmediated memory write operation and place a shellcode inside the memory. You can trigger this by this attack. Limitations. System error reporting has to be enabled on the system. From the attacker's perspective, this is a good thing because on this kind of reporting is enabled on servers most of the time. But Intel suggests to disable it. But on server parks, this is enabled because system error reporting is important. Whenever you see a hardware error, basically you get informed and you can do what you have to do. So these are enabled for RAS purposes, error handling and error reporting. And if somebody is interested, if his system supports system error reporting, you can download the slides later and you can check the fields I put you in small font size. So what kind of mitigations are? First of all, you can disable system error reporting. That's correct, right? But what happens with real problems? What happens with legitimate system errors? You cannot just simply block all of them because you don't get informed. So this is a really coarse-grained solution. There is a second attempt, a second mitigation. You can disable system error reporting due to unsupported requests from MSIs. But there is no information if all the available chipsets support it. So the conclusion is currently there is no real resolution available. So I was talking about the impact of the attack. So you know that you can hire any instance in an Amazon. And for example, you can hire a computing instance. And in a computing instance, you have a direct device access via a GPU. GPU is not a network card, but the idea is the same. You can do almost the same. And we know that Amazon, for example, uses a modified version of Xen. And as I told you, currently, there is nothing to fix in the hypervisor. The story unfolds. So, first of all, it was very tough in the sense that when I first saw the issue, I first reported to them, and somebody just came. It was Jan Bolik, and he was really nice, but he was really hesitating if it is a real problem. I'm in the sense that if it can really happen. He told me, I think your device is buggy. I told him, no. I guarantee that this is a working device. It has no problem. This is a really fancy, cool device. I like it really much because it's produced such a thing. So this is benign for sure. And after rounds of cycles with them, we involved Intel as well, if they can do anything, if they know anything about the issue. And they didn't know anything about the issue. We had to roll it back. What happened? But it took months, really. It took months for the entire investigation process. I provided them a proof of concept code, and it took them to reproduce because we didn't know that this kind of cell reporting had to be enabled. So it took time until they could verify what I was talking about. So is it a hardware or a software problem? Intel says this is not their fault. However, software vendors cannot do too much. I told you there are mitigation techniques, but this is not the holy grail that we are looking for. Public disclosure date was extended 3 times because I wanted to make sure that we know exactly what happens. I wanted to make sure that if something is going to be published, it is of value to the community. They know how to react and how to handle the issue. And the result is Accent Security Advisory and the CVE. But the funniest thing is other VMs are not mentioned generally, but I reported, for example, for the CVA, for the meter guys, to include other VMs as well. But in the CVA, only Zen is mentioned because they just handle the Accent Security Advisory, which goes for Accent systems. So what about PT fuzz? We know that PT fuzz is something that fuzzes the fields of MSI and try to find really exotic conditions and want to reveal something that is not normal, something is anomaly. And PT fuzz works, and it found other issues that is not public until now, and I'm going to publish it later. But I guarantee that this is also a hardware level thing, and this is something that is not so good as well. So, general conclusion is that either software and hardware can contain exploitable bugs, and almost impossible to find all of them, and because we lack formal methods. So even if we have something to verify, the code base is so large, first of all, that the software, current VMMs cannot be checked formally. And of course, how can we verify the hardware? And these kind of hardware behaviors that even Intel doesn't know. So I think that from the attacker's point of view, finding bugs like this can be tough, but it is even tough for the vendor how to fix it. All right, so that was the presentation. I will thank for some guys, for example, Andrea Lanzi from Eurocom, who was a really good collaborator with me, Jan Bolich, and the Intel Product Security Incident Response Team, and Pintel O'Reilly, who had good discussions about this topic. So thank you, Dan, and if you are interested in more detail, just let me know at this email address, and if you have any questions, welcome. Thanks.